So now we're going to take a look at a slightly different version of the disk method, and this is called the washer method. The big difference between the disk method and the washer method, the ones we've seen with the disk method, our shape that we're revolving sits right on the axis of revolution. There's no gap, and therefore we end up with a nice smooth disk, just like the shape of that squash. With the washer method, we're going to be revolving something that doesn't sit right on the axis of revolution, and so when you revolve it around, you end up with a little hole in the middle. All right, so if we take a look at this little visual that I have on here for you, I've got a couple different pieces that I want you to look at. So this is the shape, and this is the representative rectangle, just like we were talking about in the last set of notes. You've got the representative rectangle here. Of course, there is a gap, and so for the letter R, we're going to talk about two different radii. Capital R is going to be the outer radius, and that's the distance between the top of the shape and the axis of revolution, and then little r is the inner radius, and that's basically the radius of the gap, the distance between the beginning of the representative rectangle and the axis of revolution, and then W is going to represent the width. So you can get a nice little visual here. This is the axis of revolution. If you take this shape, this thickness and everything, and picture it revolving around that axis of revolution, you're going to get a solid that looks like a little washer, or, which we will talk more about when I see you guys, like these little mints. All right, and so if you look, which all of you guys will get one of these to kind of look at and play with a little bit, this is supposed to represent this right here. And so there's a couple things that I want to point out to you. So first of all, this little r right here is basically the distance between the center of this circle and where the actual mint begins. And then capital R is the distance between the center of this circle and the outside of the shape. And so this part right here, just the white part, is represented by this shaded part right here. And then of course, if I turn it on its side, the W is the width of the mint. All right, so we will use that as a visual aid all together tomorrow. But the volume of a washer. What the volume of a washer is basically, picture the volume of a disk, like as if there were no hole, and then subtract the volume of the hole. So it's going to look like this. So you've got pi capital R squared times W, and that's going to be what this would be if the hole were plugged in, like the whole thing. But then minus the little one. So you subtract away the hole, and then you end up with just kind of the leftovers, I guess, just the washer. All right, and so what we're going to end up doing, the way the formula will work, is both of them have a pi and a W. So we're going to factor out both a pi and W. And then we will have capital R squared minus lowercase r squared. And then the way the formula will work is it kind of follows this same order. So the formula that we see, we'll actually write it like this. You'll see the pi out front, and then you'll see the W at the end, and I'll explain why. So this part, capital R and lowercase r, you know well enough from cross sections and from the disk method, those are going to end up being functions, either functions of x or functions of y. The pi is just a constant, and so we're going to end up bringing it out to the front, and you know this is going to end up turning into an integral. We know that well enough by now, and so the W, the width, ends up being either the dx or the dy, which is why we put it last. All right, so just kind of a key here. Capital R is the outer radius, that's this distance right here. Little r is the inner radius, basically the width of the gap, and then W is the width of the washer. So to extend the disk method, we've got this region that's not sitting right on the axis. It's got an outer radius, and this is what we're doing, r of x, as like an actual function, which if you look at this bottom shape, you can see as I move from left to right, the capital R, the outer radius, is increasing as my function increases. And so it's given by a function, r of x. Then the inner radius is also given by a function, this lower curve right here. So we write little r of x. So when we revolve this around the axis of revolution, we're going to end up getting an integral. And so we get this. The pi can come out front, just like we have right here. And then as we take a whole bunch of these washers and we add them all together, we end up with the integral from a to b. We can reference this picture right here. And then our inside function will be capital R of x as a function squared, just like this piece right here. And then minus lowercase r of x as a function squared. And then the W is basically just this little width, and the width we know ends up being dx, which represents the change in x. Okay, so very, very similar to our disk method. We just have this piece in here because we have to subtract away that hole, the radius of the hole. All right, so that is our formula. I want to make a little note on here for you just that will hopefully help you out. So capital R of x versus lowercase r of x. So see how we've got this dotted line right here, and r of x goes all the way from here down to the axis of revolution. So capital R of x is the distance from the outside of the shape to the axis of revolution. Let's say the outside of the representative rectangle. Okay, so from the outside of the representative rectangle to the axis of revolution, that's the capital R. And then lowercase r, again, you can kind of see on this picture, it's this line right here. So it goes from the inside, or the bottom, I guess, of the representative rectangle. So this is the distance from the inside of the shape, or the inside of the representative rectangle, to the axis of revolution. So I'm sure you could probably guess lowercase r of x is always the shorter of the two distances. All right, I give you this little key right here just because eventually we'll be revolving around axes that are below our shape, or I'm sorry, that are above our shape. The shape will be below the axis of revolution, and so it's good to keep these two things in mind. All right, let's look at some examples. All right, so we've got this picture in front of us here. We want to find the volume of the solid formed by revolving this region by the graphs of x squared plus 1, that's this parabola right here, y equals 0, that's the x-axis, x equals 0, that's the y-axis, and then x equals 1, that's vertical line right here. So this whole shaded region, we want to revolve it around the y-axis. All right, so this one, I start off with this example because this is going to be everything in terms of y. If we're going around the y-axis, we're going around a vertical axis. With the disk method, you may have noticed that your representative rectangle is always going to be perpendicular to your axis of revolution. And so if everything is horizontal, if these representative rectangles are horizontal, everything's going to be in terms of y. One way I always remember that, you know how lines, if they're not linear, they're either like y equals lines or x equals lines. Y equals lines are always horizontal. So if you have these horizontal representative rectangles, everything's going to be in terms of y. So we can start with that. So we actually have to have two separate pieces. It's really hard to see, but can you see we've got this dotted line right here? And that's because the right minus left is not always the same. On the bottom half of this shape, right minus left is just 1 minus 0. But on the top half, right minus left is 1 minus this parabola right here. So we're going to split up into two different pieces. All right, so from 0 to 1, I actually get to use the disk method, but just like so many other times before, every time I use the disk method, I'm technically using the washer method, and I'll explain why. So my capital R of y is going to be this distance right here, the distance between the outside of the shape and the axis of revolution. And so that's 1 minus 0. And then my little r of y is the distance between the end of the rectangle and the axis of revolution. Well, since the end of the rectangle sits right on the axis of revolution, my little radius is 0, and that just means that I don't have a gap. And if I don't have a gap, I'm just doing the disk method. All right? And then from y equals 1 to y equals 2, I'm going to have a separate formula. So my capital R of y, remember, is the distance from the outside of the shape, right here, back to the axis of revolution, and that's still 1. So the outer radius is still 1 minus 0. And then my little r of y, this is the distance between the inside of the shape and the axis of revolution. And the inside of the shape is bounded by this parabola. All right, so that is going to be x squared. I'm sorry, not x squared plus 1. We've got to rearrange this function right here. This equation right here, we've got to rewrite it for x. So we're going to write x equals the square root of y minus 1. All right, so this is going to be given by the square root of y minus 1, which actually is written right there. I don't know if you noticed. All of the stuff that I'm writing down is written right there. And then technically minus 0, because the axis is the line x equals 0. All right, so we've got that set up right there. Now we're going to plug it all into a volume. Okay, so V equals, for the disk and the washer method, we're always going to have the pi out front. First piece goes from 0 to 1. That was a horrible integral sign. from 0 to 1, we're going to have capital R squared minus lowercase r squared, and then we always have either a dx or dy, and then we're going to add the second piece to it. You've got a pi, and then the next piece goes from 1 to 2. Capital R squared minus lowercase r squared. And we're not going to do any of this stuff by hand. So you would take this entire thing, plug this whole strand into your calculator. We're going to save some time while we're doing the notes because we've practiced plugging this stuff into your calculator. I will tell you that when we plug this in, we get approximately 4.712. All right, next one. These next ones, since I don't have a actual picture given to you, we're going to come up with a picture on our own. We're going to graph it, and then we're going to draw in our axes of revolution. We're going to draw in our representative rectangles, lots of little sketches that we need to make our graph complete. All right, so we've got an upside down parabola and then a line. First thing we need to do is figure out where they intersect. So we're going to set 6 minus 2x minus x squared equal to x plus 6. So first of all, you may notice they both have a positive 6, which means they cancel. I'm going to move this stuff over to the right so that my x squared can be positive. So I have x squared. If I add 2x, I have 3x right here. Okay, so I can factor out an x, and that will give me my 2 intersection points. So they're going to intersect at 0 and then again at -3. So I'm just going to plug 0 and -3 into the easier of my 2 functions. So if I plug in 0, I know they're going to intersect at 6. And I'm actually going to scale this. Let's scale this by 2. Okay, so 2, 4, 6 is where they intersect the first time. And then at the point -3, 3, if I plug that in. If I plug in -3 for x, I get 3. So -1, 2, 3, and then up to there. I'm scaling the y-axis, but I'm not scaling the x-axis. Okay, so here's my line. I know my line is going to go right through those 2 points. And then I know my parabola is upside down because I have a negative x squared. So I'm just going to do a quick sketch right there. Okay, it doesn't have to be flawless. What's really important is that you know what graph is above and what graph is below. So I want to see a handful of things. I want to see the graphs themselves. I want to see some shading to show like, okay, this is the 2-dimensional shape that I'm going to be revolving. I want to see the axis of revolution. We're going about the x-axis. So the axis of revolution is right here. And then I always want to see a little representative rectangle sketched in. So we know that if I'm going around the x-axis, that I've got a horizontal axis of revolution, which means I am going to have a perpendicular representative rectangle. All right, so I want to see all of those things on your graph. So let me talk about a couple of different things here. We want to come up with our capital R, and this time it's going to be in terms of x, because I have vertical lines, and vertical lines are x equals lines. So this whole time I have a constant upper function and a constant lower function. It's different than that first one I showed you. So my capital R of x is going to be the distance between the outside of my representative rectangle, which is right here, and the axis of revolution. All right, so that distance goes from the top of the representative rectangle, and the top of the rectangle will always be sitting on the parabola. Okay, so it's going to be the parabola and then minus the x-axis. All right, so that's going to be, I'm going to put a little dotted line out here. So that larger distance is going to be your capital R, from the top of this representative rectangle down to the axis of revolution, and the top of the representative rectangle sits on this parabola, and then minus the axis of revolution, which is just 0. And then our little r of x is the distance of the whole. So from the bottom of this representative rectangle down to the axis of revolution. So I'll mark that on there too. So this distance right here is a little lowercase r. Okay, so this bottom of the representative rectangle sits on the line x plus 6. And then minus 0. Sorry about that little dot. All right, so that's our capital R of x and our lowercase r of x. All right, so we're just going to put that into our formula. So I'm going to have a pi, and then I'm going to go from -3 to 0. Those are x values, from x equals -3 to x equals 0. And then I have my capital R of x squared minus my lowercase r of x squared, and then don't ever forget your dx or your dy or whatever you need. All right, and then this answer, what I did when I plugged this in, I actually plugged this whole thing in and then multiplied by pi later. So you can either do that, you can get a decimal approximation, or you can plug this whole thing in and then multiply by pi, and then you'll get a nice, pretty, exact answer. So this nice, pretty, exact answer is this, 243 pi over 5. Or you could do the decimal approximation, it doesn't matter. And like I said before, I'm not going to show you how to plug this into your calculator because we know by now. Just know to be careful with parentheses and exponents and things like that. Okay? This next one is kind of cool. So find the volume of a cone obtained by rotating the region under the segment joining 0h and r0. So we are going to draw a little sketch in here. All right, so 0h is going to be a point somewhere on the y-axis, and then r0 is going to be a point somewhere on the x-axis. So we are joining these points right here, and then we actually talked the other day about how if you rotate a triangle like this, you're going to end up with a cone. All right, so let me sketch on exactly what we're doing here. So this is the region that we're rotating, that whole triangle. We are rotating it around the y-axis, which is a vertical axis of revolution, which means we are going to have a horizontal representative rectangle, which means everything's going to be in terms of y. Okay, so everything is going to be in terms of y because of that horizontal representative rectangle, and horizontal lines are y lines. All right, so let's set this up. First thing we need to know is what this line is. And we're going to come up with that line just based on, point slope form, things like that. So let's come up with the slope between these 2 points. So slope equals change in y, so 0 minus h, over change in x, r minus 0. So that is a negative h over r. That's the slope of that line. And then we know that it has a y-intercept of h. So I've got y equals negative h over r times x, and then plus h. However, remember we want everything to be in terms of y, which means we need to have an x equals equation. So if we do y minus h equals negative h over r times x, and then I'm going to multiply everything by negative r over h. Okay, so these will cancel. So I'll have the x by itself equals, and then I will have a negative r over hy. And then here the negatives will cancel and the h's will cancel, so plus r. Okay, so that is our x equals line. That is this line right here. Okay, so this is the line x equals negative r over hy plus r. Okay, so we've got all of the pieces we need, everything that we can set up. So when we set this up, it's just going to be right minus left. This is going to be disk method because it's sitting right on the axis of revolution. So my volume is going to be, I'm going to have pi, and then this is in terms of y. So I'm going from 0 up to h. And then I have negative r over hy plus r, quantity squared, dy. And then because I'm sitting right on the axis, there is no little r. There's no inner radius because I don't have a gap at all. I'm sitting right on the axis of revolution. Okay, so I'm going to do a handful of things here. First of all, I am going to do this by hand, so I'm going to expand out the inside. So picture foiling these. If I multiplied one of these by itself, I would have an r squared over h squared times y squared. And then for my outside and inside terms, I would have one of these times one of these, and then I'd have another one. So minus 2r squared over h times y. And then I'd multiply r times r, so plus r squared. Okay, and then dy. So we're getting there. I know this is going to look really messy, but it's kind of a cool result at the end. So when we take the antiderivative of this, remember it's all with respect to y, so y is the variable, everything else is treated as a constant. So I'm still going to have a pi out front, and then I'm going to worry about doing the calculus. So the antiderivative of y squared would be a 1/3 y cubed, and then just toss the 1/3 in with those constants. And then minus antiderivative of y would be 1/2 y squared So the 1/2 cancels with the 2 that was there before. And then the antiderivative of r squared, since r squared is a constant, the antiderivative will be r squared times y. And then we're evaluating the whole thing from 0 to h. We're just about there, guys. I know it seems crazy and painful. So I've got a pi on the outside. Notice when I plug in 0 for y, those terms are all going to be 0. So I just have to worry about plugging in the h. So when I plug in the h for y, I have r squared over 3h squared, and then times h cubed, minus r squared over h, and then times h squared, plus r squared times h. Okay, and then just minus 0, because we know when I plug in 0, I'm just going to get 0. So let's start to clean all this stuff up. So I've got h squared, h cubed, 2 of the copies are going to cancel, leaving me with 1 copy here. Same thing here, 1 copy is going to cancel, leaving me with 1 copy here. And then last thing, see I have a negative r squared h right here and a positive r squared h. Those two terms are actually going to cancel out as well. So now I have a pi over 3 times r squared times h, which you may recognize as the volume of a cone. So a very generic calculus way to come up with the volume of a cone. I'm sorry if you don't think that's cool, because I do. All right, I think we've seen enough of these examples, so we're actually going to pass over that next example and just stop here. I'm sure that's okay with you.